So for our next topic, we're going to start looking at something called universal gravitation. To get to that, I like to start by thinking through a particular example of centripetal force. So we're going to think about the moon as it orbits the Earth. Now, if I do a quick free body diagram, the main force acting on the moon is the force of gravity from the Earth. It's also worth note that the Earth experiences a force of gravity from the moon, and these two forces are equal because they're describing that same interaction. So, the net force on the moon is equal to the force of gravity between the Earth and the moon. So, the mass, I'm going to go ahead and put AC for centripetal acceleration. The moon's speed doesn't change, but it's still accelerating because it keeps turning to go in a circular path. That's going to be equal to m times g. Now, technically, these are different m's because on the left side, that m is the inertial mass, which is how difficult it is to change the moon's motion. On the right side, this m is the gravitational mass, which is how much the moon is able to interact through that force of gravity. But even though they have different names and different definitions, those two masses are always equal, so they are going to cancel. So that means the centripetal acceleration of the moon equals g, which is the strength of Earth's gravitational field. Now, so far this year, we've been using 10 meters per second squared as our value for g. So I want to see if that works for the moon. So I'm going to go ahead and calculate the moon's centripetal acceleration. And I looked up a few values to help with that. So first, the radius of the moon's orbit, which is measured from the center of the Earth to the center of the moon, is 3.85 times 10 to the 8th meters. The moon's period, so the time it takes to orbit all the way around the Earth once, is 28 days. Now, because we're going to calculate the centripetal acceleration in order to compare it to our value for g, which is in meters per second squared, I went ahead and converted these days into seconds, and I got 2.33 times 10 to the 6th seconds. So the next thing I'm going to do is calculate the moon's tangential velocity, which is the circumference of its orbit divided by the period, or 2 pi times the radius of that orbit, all divided by the period. I punched that into my calculator and I got 1038 meters per second. So then as a last step, I went to the centripetal acceleration formula we have. So AC is v squared over r. I plugged in my value for v and my value for r, and I got 0.0028 meters per second squared, which is quite a bit smaller than the 10 meters per second squared we've been using for g. So it turns out the model that we've been using for the force of gravity has some important limitations. We've been using this equation so far, where we've always put in 10 meters per second squared for g, which is the strength of the gravitational field. Fg is the force of gravity. M is the gravitational mass. Now, some of you have noticed this formula right here. This formula is called the law of universal gravitation, sometimes also called Newton's law of gravity. It's called that because it works everywhere in the universe, whereas the version we've been using only works near the surface of the Earth. So the r here, that's the distance from the center of the Earth to the center of the other object that you're measuring the force of gravity between. So when we're near the surface of the Earth, just using the radius of the Earth itself works pretty well there. And then even if you go, for example, from the ground floor to the top floor of Tartan, you really haven't changed that distance between yourself and the center of the Earth very much, because just the radius of the Earth is so much bigger that it swamps that change that you have. M1 and M2 are the gravitational mass of the two objects involved. So if we're thinking about the moon and the Earth, M1 could be the moon, M2 could be the Earth, or you can swap those around. If you're thinking of the force of gravity on the person, M1 might be your mass, M2 might be the Earth's mass. And then this big G, that's a constant that we're going to get to in a second. Now, I do want to mention this version of the equation for the force of gravity that we've been using is related to this one. It's just that the strength of the gravitational field changes as you move farther away from the center of the Earth, which this version of the equation doesn't account for. So now let's talk about that big G. If you look at the other side of your formula sheet where we have the constants and conversion factors, there's something called the universal gravitational constant. So this is just a number that seems to be baked into the universe that tells us how strong that force of gravity is. So no matter where you go, no matter what objects you're dealing with, G always has this same number. It tends to get written as a capital G instead of this big long 6.67 times 10 to the negative 11th meters cubed over kilograms per second squared, because just a capital G is easier to deal with. So it looks like a variable, but it's a variable that always has the same number to it. So now I want to take a moment to compare this to Coulombs Law, because these equations are really, really similar to each other. So first up, they both have an inverse square relationship with distance. So they both have 1 over r squared in the equation. They both also have this constant that seems to be baked into the universe for how strong that force tends to be. For gravity, we have that universal gravitation constant. For electric forces, we have Coulomb's constant. Either way, it's this number that always has the same value. In the gravitation equation, we have M1 and M2, which are the gravitational masses of the two objects. So this number that tells us about how much an object's able to interact through gravity. In Coulomb's law, we had Q1 and Q2, which are these numbers that tell us the charge, so how much an object can interact through an electric force. So these equations are very, very parallel to each other, and they behave in very, very similar ways. I should mention this inverse square relationship also fits with the moon experiencing a much smaller gravitational field than we experience at the surface of the Earth. The moon is much, much farther away from the center of the Earth, and that inverse square relationship tells us that as you get farther away, the force gets smaller. So now the last thing I want to do is use this equation to just check. Does the centripetal acceleration we calculated earlier fit with this new equation? So what I want to do is calculate what should the strength of gravity be at the moon. So I'm going to use that G equals the force of gravity over m. And I'm using mm for mass of the moon. So according to our new equation, the force of gravity is that capital G times the mass of the moon times the mass of the Earth all over r squared. And I'm going to do all of that divided by the mass of the moon. So mass of the moon cancels out here. So that tells me that G, or little g, the strength of the gravitational field, should be big G times the mass of the Earth over r squared. So I'm going to go ahead and put in numbers. So for big G, I'm doing 6.67 times 10 to the negative 11. And then those units are meters cubed over kilograms times seconds squared. Definitely a weird unit. I looked up the mass of the Earth, which is 5.972 times 10 to the 24 kilograms. And then I'm going to do this whole thing divided by that radius. So the radius of the moon's orbit, that's the distance from the center of the moon to the center of the Earth. So I am just reusing that number. And then, if I check my units, so I've got meters squared, that's going to cancel out some of those meters cubed. Those kilograms cancel, and I'm left with meters over seconds squared, which is what I expect for acceleration, or the strength of a gravitational field. And when I put this into my calculator, I've got 0.0027 meters per second squared, which is very, very close to that centripetal acceleration I had earlier. And when I figure the moon's orbit is not a perfect circle, it's a little bit of an ellipse, it makes sense that we're not spot on with those numbers. So there we go, a quick intro to universal gravitation.